Hello, good morning everybody. In this class of D and F block element, this is the second class, we will be continuing what we were discussing last time about the different properties. So, this D and F block elements, but right now we are just concentrating or focusing our attention on D block elements, and in this particular case we are talking something which is enthalpy of atomization. So, that enthalpy of atomization such that we get atoms from all these metals can tell us two different things, that if they can have very high atomization enthalpy, so that can have different consequences, and those consequences what I told last time is that they can have high melting point and high boiling point. And the melting point part also we have discussed among the group which is chromium, molybdenum and tungsten, where we have seen that the corresponding melting points only, if we look at the melting points in degree centigrade, one is 1903, next is 2620, and for tungsten it is 3410. So, which is very high, but if we consider that there is some trend, so trend down that particular vertical line, and we also know that there will be some trend in the horizontal line also. So, whatever we find in all these cases, that means what we are discussing for the 3D, 4D and 5D elements, we can have the corresponding horizontal trend for different physical properties, and also we can have some vertical trends, and these will definitely correlate something related to the corresponding electronic configuration. So, going from chromium, molybdenum, tungsten, if we go to the extreme right, on the extreme right side we have zinc, cadmium and mercury, and by defining them in terms of the corresponding d electron configuration, we already defined that these are not in the class of d block elements. So, zinc, cadmium, mercury will not fall in this particular trend. So, they will have correspondingly very low melting points. So, zinc will have 419 degree centigrade melting point, cadmium will have 321 degree centigrade melting point, and mercury definitely we all know that this is liquid. So, it is minus 38 degree centigrade. So, down this line and on the other side we can have this, the maxima we are obtaining here. So, it is the maxima and it is the minima in this particular point. So, related to these things, that how the enthalpy of atomization can change and other physical properties also. So, coming back to the different other physical properties, we can see something where we just considered for these d block elements, that these d block elements, how they are changing for their different chemical characteristics at the same time. So, if we just consider their physical characteristics at one point of time, we will also be getting some information about their chemical characteristics, and as we all know, their occupancy of the electrons in different d cells. So, as we know for the main group elements, the s block and p block elements, the electron transfer reactions and the reactivity is also particularly say with oxygen, say fluorine and all, that can be controlled by the different number of d electrons in all these different cells. So, d cells basically and their occupancy will control the definite chemical characteristics of all these elements, and particularly these are all metals, that means the d block metals. They can also have something which we will discuss later, that occurrence of variable oxidation states, which is not very much available for other type of element, that means the main group elements. So, in a particular condition only the main group elements like nitrogen, like chlorine, they can give variable oxidation states, but these are all metallic elements or the metallic components which can have the different oxidation states. So, what we can do, we can have a particular electronic configuration for a metal ion, say iron, say nickel or copper, and during this particular process, that means the electron transfer reaction, that means the simple oxidation reaction what we have seen earlier, the dipping the zinc rod in aqueous solution or water can give some electrode potential, and due to that the zinc can lose electron and zinc can go to zinc 2 plus in solution. So, that particular tendency or inherent tendency is there, and those are due to the losing of electrons from the S cell or the D cell. When a particular metal ion, say nickel, in plus 2 oxidation state, we all know that it has a corresponding electronic configuration of 3d8. So, that particular electronic configuration, if it is stable enough, we cannot go beyond that oxidation state, that means the plus 3 oxidation state, or we cannot reduce very easily that particular oxidation state from nickel 2 plus to nickel 1 plus. But if some situation can arise in presence of some other groups which are bound to the nickel center, we can get some other oxidation state, that means electron transfer is possible. So, the nickel, like other metal ions also, the 3D elements, they can go for the different oxidation states also. If we at all get the oxidation states in 1 plus or 2 plus or 3 plus, we can say that nickel is also undergoing something where we can have the variable oxidation states for the different nickel ions. And once we get this particular compound in that for that particular reaction, so they also give compounds, as we have seen that particular dissolution or the reaction of the corresponding oxides or oxide like ores or minerals, which can give rise to the corresponding salts. When zinc oxide is dissolved in some mineral acid, say hydrochloric acid, it gives zinc chloride in solution, and during crystallization of that, solid zinc chloride can be separated out from the medium. So, it would be a corresponding compound of zinc 2 plus. Similarly, for iron, for cobalt, we can have the corresponding compounds from the metallic state, that means the metal 0 state, or the corresponding oxides or sulfides type ores, such that in these compounds these metal ions will be present as the corresponding ions. Suppose if you have a ferric compound, the ferric ion will be present as Fe3 plus, and depending upon its corresponding number of groups attached to that particular central metal ion, we can have the different structures. So, how we determine that particular structure or elucidate that structure also, particularly when we talk about the corresponding structure of the solid state structures of those compounds such as those oxides. So, we know that very two commonly occurring iron oxides, which are also available as mineral, which is hematite Fe2O3 and magnetite Fe3O4. But the solid state structures of those can be different, because we can have, these are the typical ionic compound within that oxide lattice. So, in the solid state courses or the solid state structure, you have studied these, that depending upon the corresponding filling of the solid state area or the solid state space, we have the oxide lattices, and inside those oxide lattices we have some vacancies, and those vacancies will be occupied by the ferrous ion and the ferric ion. And the particular physical properties which is originating basically from the different dn electronic configurations D1 to D9 for these series of metal ions. So, this particular physical properties, what are those physical properties? One of the most characteristic physical properties we will find it out in the solid state. We can have the magnetic properties, the magnetic moment we can determine for all these compounds, and once we dissolve this particular metal ion or the metal salt in solution, we know that most of them are colored. So, this is one more important or the most characteristic property of these D block elements, that they give rise to colored solutions. So, the coloration is another factor which we can use to identify the different types of metal ions. So, we will see from starting from vanadium to copper, we will find depending upon their oxidation states and the type of the metal ion, we have some definite colors, and all those colors can be very much characteristic for those metal salts. So, once you dissolve nickel, suppose nickel sulphate in water, we know that that will impart a particular color to the solution, and that is mostly characteristic for that particular metal ion. So, these are basically originating for the different number of d orbitals and their occupancy by the different number of d electrons. So, what we get basically about the other physical properties or more a type of other physical properties, that if we have like that of your periodic table, the left hand side on the right hand side and the upper part and the lower part. So, along this particular group, if we just see, this is the thing that enthalpy of atomization, just we are talking about the corresponding melting point of the highest possible melting point for the tungsten. So, they have mostly very high enthalpies of atomization, that is why they are having very high melting point and boiling points. And if we just simply plot in this fashion, this has been taken from your book, the NCERT book, this plot is there, but you have to go through this particular plot, at least what type of plot we are getting. If we simply go for the corresponding changes along with the atomic number and depending upon the different d electron configuration, because these atomic numbers will be different depending upon the different d electron configuration for the first series, for the second series and for the third series. That means 3D elements, 4D elements and 5D elements. So, D1 to D9 or D10 electronic configuration will give rise to the corresponding change. So, the green line what we are getting over here, so that change in green line along this one, and it is in the middle part of the thing, that means it is in the corresponding manganese system. So, manganese in the middle of this group in the 3D series. So, there is a dip basically, and the enthalpy of atomization is falling below. So, these are basically a characteristic property for this electronic configuration, which is also true for the 4D elements and also true for the 5D elements, but we should have some overall idea or overall information about the corresponding double humped nature. This is typically a double humped nature for filling off from left to right, from D1 to D5 and D5 to D9 or D10 electronic configuration from left to right. So, where we get that maximum and the middle of the series indicate that one unpaired electron per d orbital lead to strong interatomic interaction. Once we start from a D0 system, here we have no d electron, then we get a D1 system, this is the D2 system, this is the D4 system, this is the D5 system at the bottom. So, once we have, because the filling off of all these single electrons, why it is single electrons? Because we are having 5 d orbitals or the 5 d levels are there. So, the first electron will go to the first d orbital, then the second, then the third and then the fourth, like this. So, when we have more number of unpaired electrons, when in a particular situation we have 3d5 electronic configuration. We all know, and we will be discussing afterwards also, that a 3d5 situation, which we call as a high spin situation, where all the 5 unpaired electrons are occupying 5 different d orbitals. So, you have large number of unpaired electrons and 1 electron in each d orbital, giving rise to strong interatomic interactions. So, if you have a very strong interatomic interactions like that of our chromium, so chromium will have also 6 electrons, but all of them are not unpaired, but large number of electrons in chromium, in molybdenum and tungsten may lead to strong interatomic interactions. So, this strong interatomic interaction may lead to a very high enthalpy of atomization. So, enthalpy of atomization is also increasing in a order by going from left to right, and maxima in the middle indicate that 1 unpaired electron per d orbital is important. And once we have the greater number of valence electrons, that those valence electrons in the penultimate cell, that means the d level, when it is chromium, molybdenum and tungsten, we have 6 electrons in 3d level, 4d level and 5d level. So, they also lead to the strong intermetallic interactions, the strong interatomic interaction and strong intermetallic interactions, leaving behind to us a strong metallic type of bonding. So, a corresponding conduction band due to metallic bonding is achievable, and we can have the corresponding conduction band and the valence band and their separation into a typical metallic bonding type of thing, and the corresponding properties of these will also be related to their corresponding sizes. So, atomic sizes of these elements and all other transition elements are also important. If their sizes are comparable, what we can also see that this metallic bonding can also be helpful for alloy formation. So, if we can have 2 different metal centers are there and we are looking for some solid state structure where alloying can take place, or solid state mixture or solid solution or solid state solution if we can get, then there also we can have a very strong corresponding metallic interactions or metallic bonding. And this particular thing, that means the enthalpy of atomization. So, enthalpy of atomization will also be important when we talk in terms of the corresponding contribution for electron transfer. So, once we get from the bulk metallic state to the atomic state, like that of our system, when we know that a particular thing can also be vaporized to the gaseous state, and we all consider that the electron transfer or electron acceptance can take place from one side to the other in the gaseous state. Similarly, after this atomization process, that means metal in the bulk is going for M0, that means the atomic state, single atoms are there, and if we just go for their corresponding electron transfer reaction, that means we are talking something related to our scandium or titanium, whether those metal centers can be oxidized nicely to scandium 1 plus, scandium 2 plus, scandium 3 plus. Similarly, for titanium also, for titanium we can go for electron transfer because it has a corresponding atomic state electronic configuration is S2D2. So, whether we all be able to remove all the electrons in a stepwise manner, that when we move 1 electron from the S level, we will remaining with 1 more S electron and 2 D electron, but if we are able to remove all 4 electrons, if we are able to remove all 4 electrons, then titanium will go to a corresponding oxidation state of titanium 4 plus. So, this will again, once we discuss about the oxidation state and the corresponding enthalpy for the atomization also can contribute for the corresponding ionization process. So, the ionization process is also important for knowing the corresponding electrode potential of the metal. So, metal first goes to the atomic state. For the going to that particular atomic state, we require to talk about these enthalpies of atomization. So, enthalpy of atomization is important contribution for metal to go from the bulk state to the atomic state, and then that atomic state, that M0 can go for electron loss to go to M1 plus, then the second step or the third step, that means the first step of ionization or the second step of ionization or the third step of ionization is related to the different E0 values. So, E01, E02 and E03 for first electron transfer, for second electron transfer and for third electron transfer to occur. So, already we have seen that if you have a very high enthalpy of atomization, and that high enthalpy of atomization do contribute to the melting point. So, metals with having high enthalpy of atomization, also we should know that they have also very high boiling point, are noble also. Noble means that they are not very reactive. So, noble metals, we all know that gold is a noble metal, platinum is a noble metal. So, all these metallic states, so they have basically a different type or different amount of this atomization. So, high enthalpy of atomization together with the corresponding electron transfer potential, that means the standard electron transfer potential, make them a energy greedy substance or energy greedy species, where in both the two states, that means both the two processes, that one is the atomization process and second is the electron transfer process, both are very high. If both of them are very high, we are not able to get very quickly the corresponding atomic state, and also we are not very much easy to get that corresponding one where we get that corresponding electron transfer very quickly. So, metals, if it is possible, then go for the atomic state, but they will not undergo any reactivity for going to its corresponding oxidized form, that means the gold in the +1 state or the +3 state. So, along with this, that means why we are talking about this gold and platinum, because we are just discussing along with the 3D, the 4D and 5D congeners also. So, if we have these, that means we can have the early elements in these groups. So, we have a family of 3D elements, then a family of 4D elements and a family of 5D elements. So, this is 3D, this is 4D and this is 5D. So, in terms of the corresponding atomization process, we also see the high atomization enthalpy. We will also consider that is changing, so the property is changing along this line. So, within the 3D elements, we can compare their corresponding melting point and the boiling point, and there we will see that the reactivity pattern. So, from the left hand side, that means in this particular state, that means where we have the scandium, we have titanium, we have vanadium from the 3D series. So, these are basically, we can call them as the corresponding early elements. So, these early elements are highly reactive. So, thermodynamically they are reactive to what? So, if we say or if we write that they are thermodynamically reactive. So, reactive. So, what reaction? Reaction is in the atomic state also, that means scandium 0, titanium 0 and vanadium 0 will be very much reactive towards other electronegative elements like that of our oxygen and fluoride. So, what we get, if they are reactive, even if you do not have the corresponding ionic state from the elemental state, that means why they are not getting in terms of the other elements what we are defining just now as the noble elements or the noble metals. So, where we have the noble metals and why these we are calling as noble metals. So, if the early transition elements for 3D, for 5D, for 4D, all cases they are highly reactive. So, this is a thermodynamically driven process where we go for the bulk metal to the corresponding atomic state, and this can undergo corresponding oxidized form 1 plus, scandium 2 plus or scandium 3 plus. So, what we are saying over here that they are reactive, and they are reactive with say other electronegative elements such as O2 minus, such as F minus, chloride, etc. So, nature will do that particular reaction, that means the reactivity with that of O2 minus, F minus and Cl minus. We get as a result from this reaction with O2 minus that oxide minerals. So, these oxide minerals are what? Oxides and fluorides also. So, we can have also the fluoride also. Why we are getting these as the corresponding thing which can show the reactivity? Because they are harder anions. So, their charge is highly concentrated, their size is small. So, we require hard anions for this particular reactivity, and we all know that this reaction is basically coming from electron transfer to your oxygen from the gas or the environment or from the air. So, this can also be available from F2. So, electron transfer from this particular species, that means the F2 after gaining electron can give fluoride, O2 can also give rise to the O2 minus. But the ultimate reaction is that the metallic state can react with O2, the metallic state can react with F2 to give these fluoride minerals. But what about these? So, if we just simply consider these conditions or these properties to the early elements, so those properties which is directly attached to the early elements are really violated when you go or when you move towards the other end. So, noble metals will be what then? The noble metals we simply define, since we are talking about the corresponding reactive, they are extremely reactive or highly reactive, which is also a thermodynamic property. So, the thermodynamic quantity which is the reactivity towards oxygen or towards fluorine. So, that will also tell us that these noble metals are less reactive. So, if they are less reactive, they basically remain as in the metallic state, whether it is in the bulk metal state or in the atomic state. So, they basically provide something where we consider these metals as the noble metals or coinage, that means the material or the metal which is used for making coin. So, they are the corresponding coinage metals. So, these coinage metals are therefore the noble metals because they will not react, and if at all they react, they will have some tendency to softer groups, that means the softer anions such as sulfides. So, sulfide is the softer anion. So, basically softer anion, if at all they react, will provide some material like that of your oxide minerals and fluoride minerals will end up here as sulfide minerals. And that particular sulfide mineral, if at all we get, is true for copper, is true for silver, is true for gold. So, copper is the member of the 3D, silver is the member of 4D, and gold is the member for 5D. So, their reactivity is very less, So, what about if we just see on the right hand side and if we compare from that of the left hand side, and now if we just move for the other elements in the 5D and 4D elements. So, these particular group have also, suppose we have here the iron, we have cobalt, we have nickel. So, we know the other congeners, the iron we have ruthenium, we have osmium, and for cobalt also we know that this is rhodium, then we have iridium, and for nickel the next element in the periodic table will be palladium and platinum. So, if we take this particular group also and if we like to compare that particular elements with this as in terms of the atomization energy. So, in terms of those atomization energies for these, so in terms of the atomization energies for these 6 elements. So, experimentally determined quantity what we can get, they can have which are 4D and 5D elements. So, these 4D and 5D elements ruthenium, osmium, rhodium, iridium, palladium, platinum, they also have high atomization energies. So, this can therefore can control, can dictate the property of these elements. So, the whole group therefore, so this ruthenium, rhodium, palladium, then osmium, iridium and platinum. So, these 6 metals, if we form a class, they have high atomization energies when we compare their atomization energies, and they belong to 4D and 5D elements, and therefore, the last member of these, that means the platinum, we all them call that as the platinum group metals. Platinum group metals, because their reactivity would be less, they little bit they will be comparable to our copper, silver and gold, and due to that high atomization energies, they are not like this nobility in terms of the gold, copper and silver, but they are also of different properties. So, they have some correlated reactivity pattern in this platinum group of metals. So, when we see that the nature, that means when we find these in the mineral, this is the nature will give us those minerals, that means oxide minerals and the fluoride minerals we get from the nature. So, they basically occur in nature also together. So, all these elements they occur in nature together, and since they can have also comparable sizes, size is also an important factor for all these properties. So, the atomization energies are similar, their sizes are also similar, sometimes they also form very good metallic alloys. So, they are also useful for giving metallic alloys for the metals in the platinum group. So, just we have seen in that way that the metallic bonding. So, this we already told you that the metallic bonding in tungsten. So, when the tungsten is only there, so that is the highest possible melting point for a metallic species, and which can be exceeded only by the other species which is carbon. And with increase in principal quantum numbers, the spatial extent of the d orbitals increases. That means, the size of these d orbitals or the d cell in space is increasing. And since this is increasing, so if we find that one 3D orbital is approaching to the other 3D orbital to form some bond for a type which is known as the metallic bonding, such as we find in tungsten, but in case of tungsten that would be a interaction which is chromium, molybdenum and tungsten down. So, tungsten belongs to the category of 5D elements. So, you will have an interaction of 5D interaction which is higher than that of our 4D interaction, which may be present in molybdenum and which is still further less for the chromium interaction. So, as the size of the d orbitals are increasing, their size in the space, that means the spatial occupancy is increasing. So, as it increasing, they can consider for the higher degree of overlap between these orbitals. So, the trend in the overlap for metallic bonding would be 5D will be greater than 4D, which will be greater than also for 3D. So, heavier metals therefore thus exhibit many more compounds containing metal bonds. So, which is also true, because we will not have that much time to discuss about the compounds having metal bonds, but if we just simply what we are talking about the metal bonds or the metal interactions in the metallic bonding in the metal itself. So, there will be some discrete compounds, the inorganic compounds we can have, where we can have metal bonds, and sometimes we can have metal multiple bonds. That means a double bond between two metal centers, a triple bond or a quadruple bond even between these two metal centers. So, if we consider that these metal bondings are there, so other positions we also consider those as the ligands attached to this first metal, which is M1 and which is on the right hand side M2. So, other ligands will also be there, and those ligands can also give rise to the bridging unit. So, those clusters which is very common for the different types of carbonyl clusters or some simple salt like rhenium chloride salt. So, tetrachlororenate if we consider. So, that is a different type of compound or different type of proposition, but when we talk that in terms of a simple metal salt. So, if simple metal salt we get by dissolution of the ore or the mineral in acid, say zinc oxide dissolution in hydrochloric acid or iron metal rod in hydrochloric acid, will give rise to the corresponding chloride salts. So, those chloride salts are always there, and those chloride salts are not the whole thing, that means it is in the solid state entity. So, if we have metal chloride which is divalent, so metal center is in +2 oxidation state, or MCl3 metal center is in trivalent state. So, any metal salt, say it can be our nickel chloride, we will discuss in detail again. So, any metal salt like nickel chloride, like palladium chloride or platinum chloride. So, they are basically solids. So, is a solid material. So, that solid material can have some different type of structure, but when that particular solid metal salt is dissolved in aqueous medium or water, what we get? We get something, that means we have the nickel is present as nickel 2 plus, and side by side the removed chloride ions will be there, but we do not know whether we have some existing nickel chloride bond. So, in this particular case the nickel chloride bond whether it is present or not, but if we see that we are handling some nickel chloride NiCl2 only. So, per nickel, that means nickel in 2 plus oxidation state, we can have at best 2 chlorides attached to it. But if we like to have something, that means if we add more chloride, because chlorides we will be discussing at some point, the chlorides are very good ligand which can bind to the metal centers, that means the metal ion center. So, this metal ion center, if it is allowed to bind more chloride, a species can be formed which is NiCl4 2 minus. so which is tetrachloronickelate 2 ion. So, that tetrachloronickelate ion which belongs to the 3D series. So, if we go for other groups, that means we know that the series in manganese, technetium and rhenium. So, in manganese, technetium, rhenium, again all of them can give rise to chloride salts, and this particular rhenium, since it is a bigger one and it belongs to 5D element, and if we are trying to have some species like this, that means tetrachloronickelate salt of that metal ion. So, tetrachloro or further. So, tetrachloro or further metal salt will be a difficult proposition for rhenium, where if we can consider that in the discrete metal compound we can have the metal-metal bond. That means, in the discrete compound we can have rhenium-rhenium bond, we do not know how many, but you can have the interaction, and we see that we can have the chlorides are bound like this. So, apart from this, that in which geometry, because that we will discuss also later on, that if you have the geometry, so depending upon the geometry, if some space is allowed and these two rhenium groups can be pushed together like the metallic bonding in metal. So, in free metal, in the free metal, if we have the metallic bonding, so free metal will give the metallic bonding, and if that sort of interaction is still present in ionic compound, these are ionic inorganic compounds. So, we can still have some metal-metal interaction, which is only present when you have bigger 5D orbitals. So, the 5D orbitals will be bigger, then only you can have the 5D interaction, which is not present in case of 3D orbitals and which is also not present in case of 4D orbitals. So, that is why we are just considering this particular one as the heavier metals like rhenium in the group of manganese can have MM bonds. So, that is a typical proposition and that has been established experimentally by determining the corresponding structures, and structure will also tell that you can have a very close rhenium-rhenium separation, that means we can have the rhenium-rhenium bond. So, this particular thing, that means what we are just now telling, that when we get the ions, that means the nickel 2 plus we are getting from nickel chloride. So, the ions of the same charge in a given series, that means all of them are bivalent from left to right, from scandium 2 plus to copper 2 plus, if we just have. In a given series, when we get that the same charge, so the progressive decrease in radius with increasing atomic number. So, the charge is all cases will be 2 plus. So, that particular charge we are considering, that means the positive charge we are not changing much. If the size is also not changing much, what is happening? The nuclear charge is changing, the atomic number is changing from scandium to copper. So, that atomic number change, that means from scandium to titanium, what we are getting. So, increasing atomic number will give the positive nuclear charge. So, the positive nuclear charge will attract the electron density or the electrons in the different orbitals. So, the corresponding ionic size will basically go for in the decreasing trend. So, there will be more attraction due to the presence of higher effective nuclear charge. So, the higher effective nuclear charge will decrease the size of all these ions. So, that will have a particular advantage also, and we will find afterwards when we talk about the coordination compounds that the size also plays some important role if we want to have some interaction for the metal ion and the ligand. That means, the coordinate bond is forming between metal ion and the ligand. So, that particular metal ion size will also contribute to define the corresponding distance between the metal and the ligand. If it is a simple coordinate bond between metal and the water molecule, so metal and the oxygen bond is also important, and that metal oxygen bond length is also important. So, the size, that means whether it is a scandium bivalent, scandium 2 plus, and whether it is a copper 2 plus. So, the scandium oxygen bond and copper oxygen bond we can compare, keeping in the mind that what is the corresponding ionic radius of bare scandium 2 plus and copper 2 plus. And because of this, when we move for one after another electron occupancy, the electrons are entering the d orbitals, the different d orbitals. We know the 5 different d orbitals will be available to us, and each time you see that the nuclear charge is increasing by 1 unit as we move from scandium to titanium, titanium to vanadium till we reach to copper. So, the shielding effect of the d electron is also not that effective, and due to that ineffectiveness of the shielding property of the d electron, the size is basically decreasing. Why this particular radius is decreasing? Because the shielding effect is less for the d electron, and all the incoming electron starting from your scandium to copper is only entering d level. So, the nature of the electron is same, but your nuclear charge is changing much. So, nuclear charge is changing from 21 to 29. So, that basically squeezing the size of all these ions. So, this same trend is also observable for other series also. So, atomic radii for a particular given series as we see, and the variation within this series is also therefore quite small. So, unlike your S block and P block element, in the D block the ionic sizes are not changing much, and we expect the properties of all these things will be mainly controlled by the number of electrons present in the d level. So, size will not a matter of fact for identifying the corresponding behavior of all these elements or the metal ions. So, definitely what we have seen earlier, that there will be a variation in the different atomic sizes of the transition metals. So, as we move from left to right, this is once again another figure which is there in your NCERT book, and you should again recall back while you study the book that you follow the corresponding variation, that this particular plot, what is this plot, you should always be remembered in that fashion, that is the change in the atomic sizes, not ionic. Remember it, that it is the change in the corresponding ionic atomic sizes, where these metal ions from scandium to mercury say all are present in the 0 state or the metallic state or the elemental state. So, scandium 0 to mercury 0, and your radius in the nanometer scale, here in this size it is in the nanometer scale. So, why we are talking this? Because we are simply comparing, obviously the size is less for your 3D series compared to your other series. So, 3D is in green colored, then this is blue and red. So, the size of the 3D element, that means the scandium to copper. So, scandium in the atomic state, that means scandium 0 to copper 0 or even zinc 0, if we consider that, there is a continuous and a progressive variation till we reach to say cobalt or nickel, which is 3D 8 and 3D 7. So, then as we move from nickel to copper, there is a slight increase, and then up to zinc we just have a little bit higher increase to this particular value, which is below 13 nanometer to above 13.5 nanometer. So, obviously there will be an increase from the first to the second. So, as we move, as we side by side compare, so this is chromium, this is molybdenum and this is tungsten. Similarly, this is nickel, this is palladium and this is platinum. So, the difference in this particular scale on the right hand side is very easy to remember also, that if you simply compare the size in nanometer, as you are here, which is copper, and from copper you directly move to silver and then to gold. You see this silver and gold, these two are overlapping like that of our cadmium and mercury. So, this silver and gold, their atomic sizes are same almost. So, this separation between 4D and 5D atomic state for those transition metals are very close compared to the 3D. So, as we move from 3D to 4D, the radii for this 5D series are virtually the same to that of our 4D series and the corresponding members of the second series. So, this particular thing, that means this gap is very high. So, you see that this is from nickel to palladium. From nickel to palladium, this separation is much, which is the maximum separation between nickel and palladium. But between palladium and platinum, these are close by and these are very close to each other. So, the property wise, what we also expect that this particular properties which related to the atomic size of the metals will be completely different for nickel, but in terms of the size difference and in terms of the properties related to the size, the atomic size of these elements, the palladium and platinum are very close by. So, the properties related to those things will also be of similar type. So, all these things will be there, that is associated with the intervention of 4f orbitals. So, as we move here starting from this lanthanum, so the second element from the lanthanum, here we just put what is the, we are putting the corresponding 4f orbitals or the 4f elements. So, the lanthanum and the other series of 14 elements is the corresponding lanthanoids. So, lanthanoids are putting over here. So, why these two are so close? We see the jump from here to here, but we do not see any jump from here to here. This is because of putting the 4f orbitals or the lanthanoids in between, and these lanthanoids, when we give the corresponding electrons, so this associated intervention of these 4f orbitals will be there. So, what we are seeing here is that the corresponding separation for the different atomic sizes as we move from nickel to palladium is very high. So, this much gap in terms of the corresponding nanometer in this scale, that so size is increasing from nickel to palladium, but is not changing much for platinum. So, these two sizes are very close by, and this particular one we see why as we move from palladium to platinum, why this change is not there. This is due to the corresponding incorporation of the corresponding lanthanums or the lanthanides or the lanthanoids. So, after this lanthanum we have a whole 14 elements by filling up of all the 7 4f orbitals, 2 electrons in each orbital will giving 14 elements in between. So, those 4f orbitals will be filled first because these are lower in energy before the 5D series is filled. So, we start from here until we reach the end of the series, then the 5D series filling up will take place from hafnium to tantalum to tungsten to gold. So, this will basically will not contribute much, and there we see we will discuss again when we talk about the lanthanides or the lanthanoids. So, this we will discuss that the lanthanoid contraction we call something. So, instead of increasing the size, the atomic size instead of increasing, due to that lanthanoid contraction there will be some decrease, basically contraction can take place as we fill all the 4f orbitals. So, after filling of all these 4f orbitals we go to 5D series, and this particular 5D series filling up will take place again like that of the filling up of the electrons in the scandium and in the case of zirconium or yttrium. So, that will therefore not contribute much as we move after 4f. So, that is why these two series, that means the 4D and 5D series, their atomic sizes are very close by. And just now what I told you, that we can define basically also by stating this line, that the filling of 4f orbital before 5D orbitals. So, 5D orbitals we are not able to touch the filling of all these electrons from hafnium to gold. We are getting something that the lanthanoids will be filled first, and this basically results in a regular decrease in atomic radii. So, atomic radii, since we are talking about atomic sizes, so atomic radii will be decreasing in that particular fashion, and we call it as a lanthanoid contraction. So, if we see that, then we can have, because since we are considering this, so along the group we will be seeing afterwards also when we talk about lanthanoids. So, during that particular series also we have a different type of plot definitely, but after lanthanoid, because we are just simply jumping the lanthanoids, and after jumping we see the same shape is also almost same. Particularly these two are very much correlated, 4F and 4D and 5D are very much similar, only 3D is little bit different, that their exact trend is very much similar, whether you have a bottom line of F orbital, that means in the 5D case we have the 4F level, but in this case we do not have anything related to that 4F type of thing. So, this is therefore very much important, and the size is also contributing something in terms of the corresponding lanthanide contraction. So, what we get, that the consequence is there. The consequence of the lanthanoid contraction is that the second and the third D series elements, which are basically overlapping to each other, one is the member is the zirconium and another is the member of the hafnium. But if we critically compare these two values, one is 160 picometer or 1.6 angstrom and another is 159 picometer or 1.59 angstrom. So, these two sizes basically is very similar in their chemical and physical properties, and they are expected on the basis of their usual family relationship, because they are in this particular group. But the problem will come because the separation of these, that means we talk about in terms of the corresponding 4D and 5D element, but if some mineral is there, if both of them are occurring together, so size, their chemistry and their physical property similarity will not help us much for their corresponding separation of this zirconium and hafnium species. So, this density is also related to that, why we are talking so much about this size. So, density is also a relating factor for these elements. So, again these values are taken from your book. So, density in gram per centimeter cube. So, gram per centimeter cube is changing, you see there is a large variation in this density, and this density will also play some important property related to its physical behavior. So, a decrease in the metallic radius coupled with an increase in atomic mass results in a general increase in the density of these elements. So, as we see that the plot is seeing that the radius, the metallic radius is increasing and increase in the atomic mass is also increasing, but that is not overcoming the corresponding change in the radius. So, for titanium to copper, there will definitely be a significant increase in the density. So, scandium, this is titanium. So, titanium, this is titanium, and this copper is in the range of 9, basically 9 gram per centimeter cube. So, from 3 to 4 to 9 gram of this density change is definitely a significant change. So, one of the property which is directly related to the metallic radius, and we all know as we move from left to right, the atomic number is increasing, the atomic mass is also changing. So, definitely density is also will be changing, and we can consider that the metallic copper will be more dense than metallic titanium. Okay. Thank you very much.